In Chapter 6 and 7, we examine 10 common elementary steps. And many organic reactions take place by mechanisms that consist of 2 or more elementary steps, and these are called multi-step mechanisms. And a really good analogy for these are dominoes. What we see is that when the first elementary step starts, then that produces the products for the second elementary step. So another good analogy is just as letters of the alphabet can be combined in different ways to create a lot of different words, the elementary steps we've already learned can be combined in various ways to create a large number of different reaction mechanisms. So in Chapter 8, we're going to introduce 2 of the simplest multi-step mechanisms. The unimolecular nucleophilic substitution, which is an SN1 mechanism, and then the unimolecular elimination reaction, which is an E1 mechanism. And also, we're going to revisit the single-step SN2 and E2 reactions to see the similarities and differences. The other thing that we're going to do in this chapter is we're going to look at the experimental evidence that explains why we think mechanisms do what we think they do, right? And so we won't do that necessarily for every mechanism that we look at, but I do really enjoy that we look at the experimental reasons that we believe these mechanisms work the way they do. So without further ado, let's kind of jump right in and talk mechanisms. So in the previous section, in section 7.2, we saw that a nucleophile can replace a leaving group on a substrate in a single step using a bimolecular nucleophilic substitution reaction. And in this reaction, what happens is the nucleophile has the electrons. It's electron rich. This carbon is electron poor, right? Because the leaving group is super duper electronegative, and so it withdraws all of that electron density. So the positives and negatives like each other. So this negative nucleophile, the electrons come and attack that carbon. Now when they do that, we need to really use these arrows to look at how bonds form. When we show this arrow here coming here, that's showing us that a bond is formed. And so you can see the new bond is formed here. Then the leaving group leaves. If things broke up there just a second ago, I had to stop the screencast and restart it. So you haven't missed anything. We're just going to continue on. One of the other things I wanted to emphasize about this reaction is that it's bimolecular. That's where the 2 comes from. But I want you to notice that it's also just one step, right? So 2 molecules collide in one step. We can also have a nucleophilic substitution reaction that takes place in 2 steps. And this is what we call an SN1 reaction. It's a unimolecular, so that means there's only one reactant for the first step, but it is a 2-step reaction. And so what we see here is that the leaving group just leaves. That's the first step. Then in the second step, the nucleophile comes in and attacks that carbocation. That forms this bond here, right? And so we'll talk more about the kinetics of this step later. So let's compare for just a second and talk more about multi-step mechanisms. So in any reaction that takes place in multiple steps, we have to be able to distinguish the overall reaction from the elementary steps in the reaction. So the overall reaction is also sometimes known as the net reaction. So also known as the net reaction, right? Describes the changes that occur throughout the course of the complete mechanism and is obtained by adding together the elementary steps. right? So let's talk a little bit and just review. You've added elementary steps before, but I just want to review this. So to add elementary steps together, you write each step on a separate line and then cancel out species that appear in the product of one step and the reactant of another step. So for example, these two intermediates would cancel out. By comparing the mechanism to the overall reaction, we can distinguish the overall reactants, the overall products, and then the intermediates. And so a species is an overall reactant or overall product if it appears in the overall net reaction. So these appear in the overall net reaction, so they would be overall reactants. And these appear in the products, and so they would be overall products. Overall reactants are physically added together to initiate a reaction. Overall products are the newly formed compounds that are found in the reaction mixture after the reaction has come to completion. So these would be the things that we would add in the reaction flask in the laboratory, and these would be the things that we would isolate when the reaction was complete. So a species is an intermediate if it is produced in the mechanism but does not appear in the overall products or reactants. Intermediates tend to be very unstable and highly reactive. So intermediates do not appear in the overall reaction, and they tend to be very unstable. And if something's very unstable, it tends to be highly reactive, right? Usually these things cannot be isolated. Right? And so that's just, and we talked about that in general chemistry, but that's just a quick review. So we looked at the free energy diagram of an SN2 reaction, but let's look at the free energy diagram of an SN1 reaction. So when we look at the free energy diagram of an SN1 reaction, right, I want you to notice that the Gibbs free energy is plotted here on the y-axis, where the reaction coordinate or the reaction progress is plotted on the x-axis. Now, the overall reactants are located here on the far left, and unlike reaction diagrams or energy diagrams that we've seen before, I want you to notice that this has two humps, one here and one here, not one. This is because there are two separate elementary steps for the SN1 mechanism. Each step is an individual reaction that has its own reactants and its own products and proceeds through its own transition state. So the top of the hump here is the transition state, right? And each transition state, I want you to notice, occurs at something called a local energy maximum. And all that means is kind of like an energy maximum in an area. When someone talks about like something that's local, it's just in an area, right? Along the reaction coordinate. So we can kind of broadly say then, for a mechanism that contains in total elementary steps there are in total transition states. So if we have one elementary step, we're going to have one transition state. If we have two elementary steps, we're going to have two transition states. Three, we're going to have three. Because the intermediate itself is located between the two transition states, there must be n minus 1 intermediate, right? So, for example, if you had 3 elementary steps, it would be 3 minus 1. You'd end up with 2 intermediates. And so that's something that you'll see through your reaction diagrams. Now, the free energy diagram for the SN1 reaction does show 2 noteworthy characteristics of the intermediate. I want you to notice the intermediate here is higher in energy. And higher in energy means it's less stable than either the overall reactants here or the overall products here. The intermediate, though, does occur at something called a local minima. So this is called a local minima or minimum. All right, you see either one. So it's a local minimum in energy along the reaction coordinate. So the energy increases when you go either forward or backward from the intermediate along the reaction coordinate. The energy of this reaction intermediate is high because the carbon atom has lost its octet and because 2 additional charges have been created in the process. Right? So when we look here, we only have 1 charge here, but we have 1, 2, 3 charges here. And so as we talked about in chapter 7, that's going to increase the energy. Although the intermediate itself is really, really unstable, even more destabilization is created when partial bonds are introduced to the reaction to proceed either in the forward direction or the backward direction from the intermediate along the reaction coordinate. So I just want to take a moment and remind you that the transition state, that's when we start to form those partial bonds. And we cannot isolate a transition state. So even though it's really hard to isolate intermediates, sometimes we can do that, or sometimes we can use instrumentation that shows the intermediate. But for those transition steps, we absolutely cannot do that. Now, I want us to look then at elimination reactions. So we've looked at the 2 substitution reactions that we're going to talk about through the rest of this chapter. Let's look at elimination reactions for just a second. So elimination reactions are going to form double bonds. And, excuse me, in section 7.5, we saw that a leaving group and a proton are eliminated from adjacent carbon atoms in a bimolecular elimination reaction. And that results in an additional pi bond, that double bond or triple bond, between those 2 carbon atoms. And so this is just reviewing the mechanism for you. We have a generic base here, right? And this base comes in and grabs this proton, and that's going to form a new bond. When it pulls the proton back, the proton leaves all of its electrons behind. That's kind of the definition of a proton. There are no electrons. These electrons come over here to form a double bond, and that pushes off the leaving group. I want you to notice the base is not attacking the carbon with the leaving group. It's attacking the carbon next door. Okay? So when we look at this, we see that we have the 2 carbons here and we've formed a new double bond. Now understand, we can also form a triple bond, okay? So one of the big differences here between substitution reactions and elimination reactions are gonna change the bonds, right? We're gonna go from single to double. We're gonna go from double to triple, but notice substitution reactions don't change the bond type, right? We still stay with all single bonds. We just change the groups that are attached to those bonds. So that's an easy way to recognize the different steps of those reactions. Now, just like a substitution reaction can take place in 2 steps, an elimination reaction can also take place in 2 steps. And so this is the unimolecular elimination reaction. I want you to notice, right, again, that the number in the name here does not refer to the step. It refers to the number of reactants here, okay, that are starting the mechanism. So notice the step here is the same as for the SN1 reaction. The leaving group leaves. That leaves a carbocation here. The base comes in and still steals a proton from the adjacent carbon, not the carbocation, the adjacent carbon. Super duper important. These electrons come down and now they form a double bond. And that's where, of course, that's where the base comes in. And then you're going to see here, the base now has a proton. Now, as with the SN1 mechanism, we can obtain the overall reactants and products of an E1 mechanism by adding together the steps in equation 8.4. Now, I would like for you to kind of try this, and then I'm going to show you what you should see here, right? What you should see is we've got the base and the substrate. That would be what we put in our reaction vessel. Then what we would have or isolate when we were done would be the protonated base, the double bond, and then the leaving group here, okay? Notice again, the carbocation intermediate of the E1 mechanism doesn't appear here because it's an intermediate, so it's not going to show up in the overall reaction. That should be the thing that you canceled out when you were putting your two elementary steps together. Now, just like we looked at the free energy diagram for the SN1, this is the free energy diagram for the E1. It is strikingly similar to the SN1 reaction. Notice there are two transition states at energy maximas because the E1 mechanism consists of two separate steps. Also notice the single intermediate that appears at the local minimum in the energy between the two reaction transition steps here, the two elementary reactions. Finally, right, as in the SN1 reaction, the energy of the intermediate is substantially higher than the energy of either the reactants or the products. Now, this is because the intermediate has lost an octet on the carbon, but also notice it's because of the appearance of charges. We only have one charge here, and now we have three charges here. Notice we still only have one charge here, okay? So that's why this is at a higher energy. In the next screencast, what we're going to do is we are going to look at some experimental data that helps us understand why the SN1 mechanism and the SN2 mechanism have different elementary steps, as well as the E1 mechanism and the E2 mechanism. Because if you just look at the reactants and the products, there's not overall reactants and products, there's not much difference there. And so we want to really understand how we know that there are two different mechanisms happening in each case.